Hello, everybody. Thank you, Mark, for your introduction. And wow, I have to switch the gear. I'm sorry. I don't have the diagrams or equations you are familiar with. I assume most of the audience are in the optics side. So basically, what I want to say is, you guys are way more advanced than I do in a sense is you already have Alice and Bob, and then you try to communicate on the basis of Alice and Bob. So in our side, we actually are trying to find who are the possible or good parents for giving birth of Alice and Bob. This is my perspective. All right. So instead of introducing you the detailed work in my group, I basically, give you a brief introduction from our perspective, what kind of contributions we can make as condensed matter physics folks for quantum information science. This is basically what my talk is about. So in terms of materials, oops, how I all right, everybody understands that part. Actually, human civilization is always, divided into agents of materials. So that, basically reflects the importance of the discovery of any useful new materials, right? So arguably, we are now in the so-called quantum age. And there's a book already talking about this terminology. So again, as I said, you guys are already ahead of that area. So, but we are the ones who actually trying to make sense, move on, and make it more realistic about how information can flow, right? So, speaking of the quantum age, we actually have already, all right, benefited from any quantum effect. And look at the ones in our daily life we have already can experience power line and maglev train, for example, or when people go visit hospital, and some of them may need MRI. And more recently, of course, you all know this IBM Q. So with all of this technology, it is actually based on the material which is called superconductor, right? So superconductors give us a leveraging without any resistance. That's why it is extremely useful for power line or power transmission. Or you can use for other very high precision measurements or like MRI or like other technology. And no need for me to stress about IBM-Q. I'm sure quite some of you have already played with it. All right, from this point of view, let's boil down a little bit about something you're probably more close to what you are doing, IBM-Q. When you boil down, it looks a big chunk, but most of it is just for cooling down. All right, the heart of this machine is quantum chip, right? And this is something probably is more familiar with you, but come down to the unit, which is just that little corner called Josephson junction, which is based on superconductors, right? So it is just that little part, all right, make it justified for the capital Q. Okay, so this tells us, materials which are really extremely tied to carry whatever information we are interested in, particularly quantum information. And so at least from the current status, IBM-Q proves the traditional, we call conventional superconductors can do something good for quantum information science. Here, basically people use magnetic flux to build up qubits. All right, among superconductors, it's also a big family. It's over 100 years old. And so in the past 2 decades, much more attraction is actually coming to a special group of superconductors, which is called topological superconductors. Why? It's because it will or it hosts Mariana Fermions at the boundary states. So you may not be familiar with the top line topological superconductors, but this is something I'm sure you are familiar with. And so what happens is in this special class of superconductors, and they have a special surface state. All right, so the surface state is actually hosting a single particle, but for the bulk, which is represented by this deeper green here, or forest green, which is the superconductor. In the superconducting state, electrons are super good friends. They are paired, we call them. So now what the system experiences is at the boundary, and the pairs have to be separated. And that comes up with electron hole pair, and we call Andreev boundary state. In this case, it would satisfy Dirac Hamiltonian, and this will automatically, generate massless, chargeless Mariana particles. And this, as we know, the characteristic of Mariana particles would be what? They are their own antiparticles. And with this, you don't need to worry about whether they are entangled or not. And it's naturally embedded, inherent. So in order to have this kind of state or hosting material, it can be other naturally formed superconductors, but it requires a special pairing mechanism, so-called spin triplet, or more in short, P-wave superconductors. Another way, in last a decade, theorists mainly, have been trying to make it other way, because I will show you in the next slide, the naturally formed spin triplet superconductors are so real, unusual. So there are other ways we can use, artificially constructed system to host such boundary states. All right, so regarding Mariana fermions, the natural ones which are most promising so far is one, the helium, the so-called superfluid state of liquid helium. And that hosts the so-called P-wave state. But this number one has to go down to below 1 Kelvin. The major issue is, again, it's a superfluid. That would be tough to make device based on superfluid. The only other promised solid material is showing here at the bottom left corner, and that it is namely strontium 2, ruthenium, oxygen 4. And that has superconductivity below 1.5 Kelvin. I started to pay attention when I was a postdoc back to more than 20 years ago, because that was my major project. And we try to use a device type of structure to prove its P-wave superconductivity. And this, amazingly, after 30 years of discovery in 90s, people actually investigated this material even more than before. And so this probably is potentially the first solid material for the quantum information-based devices. Another thing on showing in the right-hand side is much more durable. In a sense, you just add normal superconductors or so-called singlet superconductors, which we have tons of them, and then being fabricated on top of so-called topological insulators. I will introduce very soon. When you do this, there will be an interface. At the interface, again, because of this spin orbital coupling, which is in the gray area here, and the Cooper pairs offered by superconductors at the interface, and you have to make a breakup of Cooper pairs, we call. And then that would be similar case as we have seen in the P-wave superconductors. And that will generate Mariana Fermions or Mariana zero energy mode. All right, so so the most important thing is this is a special type of, we call quasi-particle, and that would be extremely attractive for topological quantum computers applications. All right, just recently, in the late last year, in Physics Today, and I'm sure many of you have that in your desk. Probably you did not bother to take a look this article about Mariana qubits for topological quantum computing. All right, so basically you can generate the Mariana modes at the edge as demonstrated on the right-hand side. And so since they are naturally entangled, and you can generate all possible states in between or phases if you wish. So as the abstract show here, researchers are trying to store robust quantum information in Mariana particles and are generating quantum gates by exploiting the bizarre non-abelian statistics of Mariana zero modes bound to topological defects. So it's not really topological defects, it's just, again, the boundary states. And, so the actual Mariana zero modes is, just occurring in the boundary states for any possible, applications. So with that, I'm aware of this bet. Not long ago, sadly, our colleague is gone, but we hope someday in 10 years or 9 years now, there is some answer to this. So the major bet is whether topological quantum computing be existing by year 2030. And so, of course, whenever you have bet, one is up, one is down. And so I'm not going to details about the actual bet, but this is basically showing you, there are, two schools of thoughts regarding topological quantum computing, or more so about topological materials. So now I come back to briefly introduce about topological phase, because this is what, people use one sentence to say. Topologists study properties of objects that stay the same despite deformation. Yes, the description is overall true, but regarding, how much people's understanding about such concepts are still kind of, questionable. So I would like to just briefly say the topological phase, which is basically one form of matter. And if you are familiar with Dirac Hamiltonian in one term, and that includes this spin matrix dot product of momentum. And what happens when the topology plays a role, this term would no longer be zero. And that's how it comes into play with every physical properties. All right, no need to say this is a quantum matter. And as I already mentioned, it's interesting because it's non-commutative geometrical phase. And also, there is something I don't go to detail today, Barry phase, or just to say local geometrical phase. When it happens, I'm sorry, when it goes this, and when you do the integrals over the local geometries, and your properties change, and we'll have the protection. These properties will have protection of topological topology. So that's why the materials which have special topology would be very interesting and more so technologically relevant. All right, come back to the Dirac equation. You guys are more familiar than I do. So what happens is it would generate the consequence that the energy would have a linear dispersion with the angular momentum. I'm sorry, with the momentum. So this is a famous Dirac cone. So when you have the electrons residing in such a Fermi surface, and the spin momentum is locking. So that's why spins have to be aligned in such peculiar way and generate a non-zero phase. We call it Barry phase. Anyway, more so is it would be the electrons would be active, essentially massless at the Dirac point, and spin-wise would be acting as magnetic monopole, and we call Dirac monopole. Right. So overall, the topological materials, their properties, as I briefly mentioned, are protected by their bulk. And so most important to us, to this group of people, is the surface of those materials. And one can harvest the particular ones, particularly the excitations, happening in those, on the surface of those topological materials. All right, so why, again, we are so into this is because when those excitations or particles on the surface, they are protected by the bulk, and so they would be decoherence free. And I'm sure because in your last quote, we have our colleague Dan Shihe who talked about, I'm sure he also brought this concept up. So ideally, these particles would have not suffered any decoherence. And as we already talked about that, we could have, a manageable quantum states to form qubits, right? So would it be really wonderful platform for building up quantum devices, or more so to carry out quantum information. All right, if you don't mind, I really like this quick clip, and that I want to tell you my perspective why I want to show you this. Please bear in mind, just take this as kind of a short break or entertainment.
Your guest lecturer, Dr. Sheldon Cooper. I was expecting applause, but I suppose stunned silence is equally appropriate. I agreed to speak to you this evening because I was told that you're the best and the brightest of this university's doctoral candidates. Of course, that's like saying you're the most important electron in a hydrogen atom. Because you see, there's only one electron in a hydrogen atom. Best and brightest, my sweet patootie. All right. That's Let's begin. Show of hands. Who here is familiar with the concept of topological insulators? Don't kid yourselves.
All right. Okay. The reason I show you this clip is because on the one hand, you can see everybody raised their hands when they were asked whether they are familiar with the concept of topological materials or insulators. That's a really good sign, means people are aware of this group of materials. But on the other hand, as Cooper would say, you know, he did not believe that because a lot of things going on. So that's my main point. So let's just again go spend another minute about this. Basically, the topological, the other insulators or superconductors, we, I already, had some kind of touching base on these two type of materials, but they both share their common features. Number one, the bulk is gapped. For superconductors, of course, it's superconducting gap. For insulators, it is insulating gap. And so the surface, which is represented by yellowish here, it has no gap, regardless whether it's a superconductor or insulator. All right, so the thing is for topological insulators, you would have edge current, which is dissipationless. So when we have no dissipation, and that means what? We are not going to lose any information. So in other words, we would not expect any decoherence. So that's the spirit of this kind of materials. All right, so we have been studying this kind of materials, both topological insulators and superconductors for decade. So the basic idea in the field is how to make them truly robust for actual applications. All right, so one thing is on the surface, as I just introduced, you have the spin polarized current, which can be obtained from such material system like topological insulators, just because of the spin momentum locking, and they have to be organized in a really ordered way. And so spin up would go one edge, and spin down would have to go another side. So with this kind of arrangement or forced arrangement, so we could basically leverage these properties. And I can give you brief little bit more about what potentially application could be. And this one is already introduced to you, and which is probably more doable experimentally by having heterostructure as shown here, and to create the Mariana states, and which can be integrated into what quantum qubit chips. Another thing probably easier, I bet Omar's group already uses such thing, photon detectors, and we can make it probably a higher resolution and so on. And you can, of course, we talked a long time about possible magnetic devices, memory devices based on those materials. And we can do the field effect transistor so that we can harvest multiple states as one desires. All right, so it's 10 o'clock. I guess I need to wrap up. Anyway, so also our group also does is so-called Weyl fermion system. This is when the Dirac system breaks the degeneracy by either lower down the inversion symmetry, which is crystal side, or time reversal symmetry, which is magnetism, which can break down what really now you can see is monopole flux or chiral charge, because magnetic flux would be separated by having monopole in and out. So that would gives us one more degree of freedom to play with those kind of particles. And so just to give you a perspective, that would be easier to distinguish between Dirac semimetal and Weyl semimetal. This can really give us a so-called spin resolved situation when we play lower symmetry, either crystal symmetry or time reversal symmetry. So when you have the spin resolved capability, and we could harvest, so-called chiral magnetic effect. People already can get spin polarized current out through such a system. All right, and there are more things going on, and I'm running out of time. I'm sure you heard this terminology: spin liquid, spin glass, and spin ice. In the past 2 years, we have been doing quite some spin glass type of material studies. And so all of those allow us to generate a bunch of quantum states, which can be used for carrying quantum information. All right, so in our most proposal, we actually collaborated with a bunch of chemists proposing study a special group of materials called single molecular toroidal materials. And so as illustrated here in this corner, there are certain molecules, there are a bunch of ligands around, but what happened is for certain metals there, showing you here is actually disposing. They form naturally toroidal moment. And it's just, structure wise so beautiful. This, it would be, having whatever counterclockwise, and the bottom would be also counterclockwise. In the middle could have something else that generates tons of spin states. And why we are focusing on this or into this group of materials is because they have been found the decoherence time is pretty long, or long relaxation time, so that the qubits can do a lot of things in this relaxation time period. So in other words, another thing is because we call why they are called single molecular material system, because between molecules their interactions are probably negligible. So that would make much easy controllability and scalability. All right, so with that, I just leave my summary here. Basically, condensed matter physics people are trying to leverage the spin degree of freedom for quantum information processing. And so in order to make it effective and make you guys happy, we really needed to have fundamental understanding about these materials, how the information can be carried out and being lasting for a long time. And so I'm sure we are part of your group for making discovery-based research and to advance the quantum information science. Thank you.
All right, thanks, Rongying, for the talk. We hit the time of the break. I think we can have one question. I see that Ilya raised his hand. Feel free to unmute yourself and ask a question.
Okay. Rongying, you put the Physics Today things by Covenhagen. Of course, Covenhagen made other headlines recently.
Yeah.
The statement of Majorana's has been withdrawn. So in certain geometries. So the question to you, an experimentalist, is what actually would be a smoking gun experiment that tells me that I have a Majorana particle in a particular setup? Because, zero bias peaks appear everywhere, as we know.
Right.
So so from your perspective as an experimentalist, what should I look for to believe that there is a Majorana?
Mm-hmm. I had the same question.
That's cool. And I'm sure you are not happy because I'm probably also have a hard issue in terms of what is the smoking gun, for saying this is for sure Mariana mode or particle, whatever people want to state. And as you said, I mean, I would take zero STM zero energy mode as my best bet. But like you said, the this zero energy mode is everywhere. But I would consider in combination with the structure, particular heterostructure, plus the probe, one would not probably have much other mechanism to explain the zero energy mode seen in the other P-wave superconductors or the heterostructures. This is my perspective for now.
Okay, thanks.
Sorry, Ravi, you have a question, right? You are muted. You are muted.
I asked Ravi to unmute, sorry.
When you talk of linear dispersion, as you said, the energy going linearly with K, that implies masslessness. What is any real experimental evidence of an electron's effective mass being zero in your system?
We have probably, if it's not 10, we have probably 8 papers. We claim the multiple.
I see.
We do, I did not bring up because I don't want ball fox here. What my lab does is we do the quantum oscillation measurements, either de Haas-Van Hoff type or Chepanev for de Haas type. When you do that, you observe quantum oscillations, and then we plot this data, and they have geometric quantum oscillations, and then we fit our oscillative data to Lifshitz equations, and that gives us the effective mass.
I see.
Yeah.
Right, but also
quite some papers practicing along this line. Yes, Ilya.
Yeah, so what Rongying described is her experiments on the nodes in the bulk. If you're asking about the surface in topological insulators, which is what she showed, we have angle resolved photo emission data.
I see.
So that you can see directly. You actually see the dispersion of the peak. So when you go to the bulk to vials, which is what Rongying studies, you need to do this more elaborate things. But for topological surfaces, there is as direct as you can.
I see.
Right. ARPAS directly shows you such a linear Dirac band.
Thank you.
All right, so we're cutting into the break now. What I'm going to do, if people want to continue discussing, I'm going to make a breakout room. I haven't done this before. And I'm going to